Welcome once again to this class of power system dynamics and control. Today we'll further discuss the transient stability analysis. So last class we have discussed repeating whatever we discussed in the last class. Euler's method, modified Euler method, and Runge-Kutta method. Explicit because the variable xn should be known to compute xn plus 1, where method it is not required. Okay. So the problem, what are the problems is in case of unsymmetrical fault? Because this, when the in case of three-phase balanced fault at a bus, the row and column of the system admittance matrix corresponding to the faulted bus is removed as the voltage at the bus is 0. Okay, when the fault happens, three-phase fault occurs. If it is a balanced fault, then easily we can modify the equations or the model. Like corresponding to the faulted bus, we can remove the voltage equation, we can remove the admittance, remove the column and row of the admittance matrix. By that way, we can model the network equations. And the power balance equation also at the faulted bus will be removed because it will be 0 in that case. So this incorporates the effect of a three-phase balanced bus fault, right? In case the fault at some location, the transmission line, then if the fault is not at the bus terminal, substation, you can say, but it is on the transmission line, then how will model? Then the bus admittance matrix should be changed. Okay, so the bus admittance matrix will be. We'll see some examples in Kundur. You can find it. So in fact we'll discuss how the bus admittance matrix will change and the network equation also will change. When the fault is at the middle of the transmission line, it is sorted to the ground. In fact, it will behave like a pi model. So obviously the elements of the admittance matrix and the network equation will change because of the change in the topology. So then the rest of the procedure will remain same. So this is in case of the balanced fault or three-phase balanced fault, you can say. But when there is an unbalanced fault, so this procedure we cannot follow. Whatever procedure we are talking about, like changing the equations and modifying the admittance bus matrix. So in case of really, so instead of symmetrical, in this case, instead we can use the symmetrical component theory. How we can use the symmetrical fault, we'll see. So before that, let us revise the symmetrical component used analysis unbalanced faults. In the method of symmetrical components, unsymmetrical current phasor, symmetrical set of voltage or current phasor is resolved into symmetrical sets of components. That is the main idea, main process is followed. So what we do is we X in terms of the symmetrical components. There are three symmetrical components. One is zero sequence component, positive sequence, and negative sequence component. Already, I think you have studied in your BTech course also. I think Abhindas and Hare Krishna also have studied. They might have studied in the fault analysis part of their previous courses. So just revising those parts. So the unbalanced three-phase system is resolved into balanced systems of phases called positive, negative, and zero sequence components. Okay, so represented by ABC, and the symmetrical components represent these symmetrical components. Let us find an operator A. That is, we are discussing the symmetrical component methods. Okay, so each of the phase voltages I can represent the sum of the symmetrical components. Like VA, I can represent VAO plus VA1 plus VA2. Similarly, VV I can represent VVO plus VV1 plus VV2, and VC, VCO, VC1 and VC2. These are the symmetrical components. They are in fact the balanced components. Each of the sequence, if you'll see, positive sequence, negative sequence and zero sequence. In positive sequence, we can see the sequence is exactly equal or exactly similar to the actual system, right? And the negative sequence component is opposite to the positive sequence component. If it is clockwise, VA1, VV2, VC1, this is anti-clockwise. The sequence is anti-clockwise. Okay, so this is all about the symmetrical components. So we are discussing. You can see, seeing the figures. Positive sequence, negative sequence, zero sequence. Okay, so now I am showing the representation of voltages, unsymmetrical voltage or any voltage using the symmetrical components. Okay, so this is how we represent. So VA I can write summation of VAO, VA1, VA2, VV equal to summation of VVO, VV1, VV1 plus VV2. Like in the last slide I have shown this. These three equations. Now these three equations I can present in the matrix form this way, right? Okay, using this A operator. Is it visible?
Yes, sir.
Okay. Now in the matrix form I can write VAVC equal to T of V012. T is nothing but that transformation matrix. That is 1 1 1 1 A square A 1 A square. If we'll take the inverse of T, we'll find that 1 by 3 of 1 1 1 1 A square 1 A square is it's a similar matrix, just one or this just the elements are interchanged and it is divided by 3. So it can be observed that for a balanced system, obviously for a balanced system, the negative sequence component and the zero sequence component will become 0. Okay. And only the positive sequence component will remain, which will be equal to the phase voltage or the voltage of the system. Okay. Now similarly, the currents can be represented. The ABC or the three-phase current can be represented using the sequence components. The complex power also can be represented. So the three-phase power generally we write in this form, right? VABC transpose IABC conjugate. So now I can transform this ABC into 0, 1, 2. That is the sequence component elements. So if I'll convert this VABC, I can write it transformation matrix into V of 0, 1, 2 transpose into T of I 0, 1, 2 conjugate. So if we'll take the just manipulating, we'll get V 0, 1 to transpose T transpose T conjugate I 0, 1 to conjugate. So T transpose and T conjugate, they are nothing but it will give 3. Okay, so it will become 3 times V of 0, 1 to transpose and I 0, 1 to conjugate. So it is very easily we can understand or we can observe that from the above equation that the complex power also can be computed from the symmetrical components as well. If we know the symmetrical component variable, so we can compute the complex power as well. So just as three-phase voltage and currents are expressed in terms of symmetrical components, the three-phase impedance can also be expressed in terms of positive, negative and zero sequence impedances, right? In terms of positive, negative and zero sequence impedance. So three-phase impedance means like the impedance of a transmission line or impedance of a transformer. If it is given, we can transform, we can convert this into the component sequence components as well. Let us say consider a transmission line, simple series impedances. The series impedances are ZS is the self impedance and the mutual impedance between the two phases, let us say Zm. Then we can write the equation, voltage equation uh, in the transmission line. The VA, in fact, the voltage difference between the two end of the transmission line. So VA, I can write ZS IA plus Zm IB plus Zm IC, and similarly VB and VC I can write. So converting this voltage and currents into the symmetrical components, this will lead to this equation, right? So VA, VB, VC, I can write T of VA0, VA1, V2, which is so the T inverse of this. VA, VB, VC, I can write it as sorry, VA. There is a little mistake, I think. VB, VC, I can write it as T inverse VAO, VA1, and VA2. Okay. So, okay, so this will be T and this will be T inverse. Okay, just you can mark it. So this will become T inverse. This is nothing but T inverse, and this is your T. Yeah? This is the mistake, I think. So VAO, VA1, VA2. I can write this as T inverse ZS, ZM, 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 ZS, ZM, 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 ZS. This is the matrix, Z matrix into T times IAO, IA1, IA2. So if I will multiply this T inverse into impedance matrix and the T matrix, I will get this equation. Okay. I'll get this sequence impedance matrix, which is nothing but very segregated equations will get ZS plus 2ZM and all the diagonal elements. Is it visible?
Yes, sir. I think it will be T into T inverse, then IA, I naught, IA1, IA2.
The equation is correct.
Equation is
Correct.
correct, sir.
Yes, sir, it is, sir. It is correct, sir.
No, no. VA, VV, VC is VA, VV, VC is nothing but T of VO, VO, V1 and V2, right?
Yes, sir.
See
But we
here.
have to write in terms of VO, VA2, VA1, and VA2. So we'll multiply with the
We replace
inverses.
that positive means all the phases voltages in terms of sequence.
No, VA, VV, VC,
That's
if
correct.
we'll write in terms of VA, VA1, VA, VV, VC is equal to what? VA,
T
VV,
transformation into those sequence components.
VC equal to T of VAO, VA1, VA2, right? Okay. So I need to substitute this, T of this here, right? This T of this will be substituted here. And T of this will be substituted here. Okay. If we'll substitute this here, it will come T inverse, right? Are you getting?
Yes, yes, sir. Yes,
Yes,
sir.
sir, it is correct.
T inverse, right? T inverse
Okay,
Z
sir.
matrix, then T of understood. Okay. I think that was a mistake in the somehow. So
We are getting frequent question in GIT, sir.
sorry. Be louder. Anybody speaking anything loud? Not audible. Any question or
Questions are
comment?
very questions
Huh?
are very frequent in GATE in this using this concept.
Sorry. Little loudly you can speak or you use your microphone. Who is speaking?
Nothing,
Hare
sir. It's
Krishna. Hare Krishna. It's fine.
yes, sir. It's fine.
Okay. Now we got this sequence impedance matrix. Okay. If we'll multiply, we'll get this. Now we can see the zero sequence impedance is ZS plus 2Zm, and the positive and negative sequence impedances are Z1 equal to Z2 equal to ZS minus Zm. In transformer and transmission lines, the positive and negative sequence impedances are same, almost same. So because they are series impedances, if we'll neglect in transformer, if we'll neglect the shunt branches, then it almost only the series impedance will be there. And in power unit, obviously it is only the series impedance it will show in the transformer. It is similar to the transmission line. So in case of rotating machines, unlike the transformer and transmission line, like in case of synchronous machine or induction machine, we'll see the positive and negative sequence impedances are not same, like in transmission and transformers, right? Transmission line and transformers. The zero sequence impedance is present only when there is a path for the zero sequence current. If there is no path, that means suppose we have a transformer, star connected transformer, but the neutral is not grounded, then the zero sequence current will become zero in that case. Similarly, if we have a synchronous machine, star connected, and the neutral is not grounded, the zero sequence component will become zero. So therefore, in order to get the zero sequence component, the neutral must be grounded, whether it's a transformer or synchronous generator. In case impedance Zn is connected between the neutral and the ground of a transformer, then the zero sequence impedance will become ZO plus 3Zn. If it is solidly grounded, then it is obviously ZO. If your neutral is grounded through the impedance Zn, then your zero sequence impedance will become ZO plus 3Zn. Okay. So in case of ungrounded neutral, zero sequence currents cannot flow, hence the network configuration has to be taken into consideration to check the zero sequence current path. Now the unsymmetrical faults can be analyzed through the symmetrical components. In case a fault occurs at a particular location in the system, then the rest of the system can be represented as a pre-fault balanced Thevenin's voltage with a Thevenin's equivalent impedance. Okay, so when we do the fault analysis, I think everybody has done in his BTech courses. When you do the fault analysis, we find the equivalent circuit at the fault point that we call a Thevenin's equivalent. And when we do find the Thevenin voltage at the fault point, when we see the network from the fault point, and we determine the Thevenin equivalent circuit, we'll find the Thevenin voltage and the Thevenin equivalent impedance in series. Okay, and that plays very important role in determining the fault current. Let EAVC be the Thevenin's voltage. Let us consider the network, and we found the Thevenin's equivalent for the network, and the Thevenin's voltage as seen from the fault location is EAVC, and the Thevenin's impedance is ZAVC, and VAVC and IAVC are the fault location voltage and current. Then the equation we can write at the fault point is VAVC equal to EAVC minus ZAVC into IAVC, where EAVC is nothing but the Thevenin equivalent, which is a balanced voltage, right? Which is a balanced voltage source or balanced Thevenin equivalent voltage source, and ZAVC, IAVC, right? So this VAVC is the voltage at the fault point, which may or may not be balanced. It depends upon the type of fault. If your fault is unbalanced, then this voltage will be unbalanced. This VAVC will be unbalanced. So VABC, I can write it as EABC minus ZABC into IABC, right? So expressing this equation into symmetrical components will lead to this equation, right? Because this EABC is balanced, so therefore your, if we'll convert this, your negative zero sequence and negative sequence component will be zero, except the positive sequence component, which is nothing but equal to the phase voltage of the Thevenin voltage, right? And the components of the voltage at the fault point, the sequence component voltage at the fault point will be VAO, VA1, VA2, and similarly your impedance matrix will be a diagonal matrix, that is the sequence impedance matrix, and the current similarly, right? So if we'll convert the above equation just by transforming into the sequence component, you will get this matrix, right? So very easily you can convert, just substituting VAV is equal to transformation matrix into sequence components, you can find this equation very easily, right? Since the rest of the system is represented as a pre-fault balanced Thevenin's equivalent voltage source, the zero and negative sequence voltages will be zero. Already we discussed this. This is true for the power systems because the synchronous generators will always be producing balanced voltages and hence will only have positive sequence voltages. From this equation, the fault currents can be computed for different unsymmetrical faults like single line to ground fault, line to line fault, and line to line to ground fault. So then from this equation, we can easily find the fault current, okay, which is desired for our analysis. Now if we'll see a system of network, we can represent as equivalent circuit. This is your equivalent circuit, and let us say there is a fault point, like ABC is represented, this is their fault point, let us say, right? And under balanced fault condition, I can represent the network like this: zero sequence, positive sequence, and negative sequence network. And which in the equivalent circuit form, I can represent like ZO. The voltage source here will be zero because it's a zero sequence network. And for negative sequence, for positive sequence, it will be VF will be equal to your EA, okay. And for negative sequence, it will obviously zero because it's a balanced fault. So and the sequence networks, we can see they're all separate, they are not interconnected, they have no relation with each other, they are decoupled because of the decoupled equation, we get the decoupled network, right? Now we'll see the single line to ground fault, which is unsymmetrical fault, and let the fault be on phase A. Then we can represent this fault symbolically, or through the figure. We can see here the fault is at phase A through an impedance ZF. But here for simplicity, we are considering ZF equal to 0, which is the bolted fault, single line to ground fault. Now the conditions are VAG equal to ZF A, which is nothing but equal to 0, because ZF we are considering 0, and IB equal to IC equal to 0. Okay. Now the conditions are mentioned here: VA equal to 0 and IB equal to IC equal to 0. So hence we can write the equation. So VA, I can write VA1 plus VA2 plus VAO, which is equal to 0. And similarly, your IA1 equal to IA2 equal to IAO equal to IA by 3. How you can find this? Just by substituting the sequence components in this equation, you will find this equation. Okay, so it's easy to find, we can do it easily. And now substituting these two equations in this equation, just substituting this in this equation, in this substituting this in the above equation, we'll find that EA minus Z1 IA1 minus Z2 IA2 minus ZO IAO equal to 0, right? We can do this. You can try also. You can find it, right? Now in this equation, if we'll substitute the currents are all are equal. So by substituting IA2 equal to IA1, IA1 equal to IA1. So now we'll find IA1. IA1 is nothing but EA by Z1 plus Z2 plus ZO. So this is the equation for IA1, which is the sequence component of the, if we know IA1, we can find IAO and IA2 because they are all equal. And then we can find IA, which is the fault current, right? Okay. Similarly, if we'll do the analysis for line-to-line fault, let us consider line-to-line fault between phase B and C, considering a fault impedance ZF. And here for simplicity, we are considering ZF equal to 0. Now, under this fault condition, your IA equal to 0 and IC equal to minus IB, and VB minus VC is equal to ZF IB, that is nothing but equal to 0 because ZF equal to 0. Under that condition, I can say VB equal to VC and IB equal to minus IC and IA equal to 0. So considering these equations, if I'll substitute the sequence components in these three equations, I'll find VA1 equal to VA2, VAO equal to 0, IA1 equal to minus IA2, and IAO equal to 0. Now if I'll substitute the above equations in this equation, your network equation, we'll find this equation, that is IA1 equal to nothing but EA by Z1 plus Z2. So from this equation, after finding IA1, you can find IA2 and IAO, which can be used to find the fault current, which is line-to-line fault current between phase B and phase C. Okay, so again, considering another type of unsymmetrical fault, that is double line to ground fault. Similar analysis we can do here. ZF we're considering 0 here, the fault impedance, and the conditions we found from this fault type is IA equal to 0 and VVG equal to VCG, that is equal to ZF IB plus IC. If we are considering ZF equal to 0 for simplifying the analysis, so therefore it will become 0. VV equal to VC equal to 0. Under this condition, we can find that if we substitute the sequence components in these two equations, then we'll find the sequence equation, the equations corresponding to the sequence components like this. And just by substituting this here, VA1, VAO and VA2, or VA1 in terms of EA and IA1 and Z1, we'll find this equation. So EA minus Z1 IA1 equal to minus Z2 IA2 equal to minus ZO IAO. So from, if we'll substitute each individual voltage equations in this equation, we'll find this equation. Now from this equation, if we'll eliminate IA2 and IAO, we can easily find IA1. So just by eliminating, we'll see the equations. IA1 remained like this, IA2 we have substituted from this equation, and IAO we have substituted from this equation. So IA2 and IA1 both are substituted. Then you will find this equation, and from this equation you can find this IA1, that is nothing but equal EA by Z1 plus Z2 ZO by Z2 plus ZO. So this is the double line to ground fault equations. Now if we'll see all the fault current equations in using the sequence components, IA1 we found for single phase to ground fault as EA by Z1 plus Z2 plus Z0, and similarly for line to line fault case, IA1 we found EA by Z1 plus Z2, and similarly for line to ground fault we found EA by Z1 plus Z2 Z0 by Z2 plus Z0. So then we can say that these impedances are the effective impedances seen at the fault point. These three impedances are the effective impedances. So from the above equation, it can be observed that the power system during unbalanced fault can still be represented as a positive sequence network with appropriate effective impedance connected at the fault location. And rest of the transient analysis can be done as explained before. As we have discussed before, rest of the transient analysis can be just by just by representing the network in the positive sequence network form, then we can do the analysis. So our main objective here is we have to convert the representation into positive sequence network form. Then we'll do the analysis as it is what we have done earlier using the implicit method and the explicit method. So the effective impedance in the different fault condition we found from these three equations. For the single line to ground fault, it is Z1 plus Z2 plus Z0. Line to line fault, it is Z1 plus Z2, and line to ground fault, it is the effective impedance. When the transient stability of a system is assessed for a large disturbance like fault, either balanced or unbalanced, by solving the differential algebraic equation through numerical methods mentioned above, and the period of interest is typically 2 to 10 seconds. If the system doesn't settle down to post-fault stable operating point within time of interest, then the system is said to be unstable. So from this analysis, we have to use the numerical method just to see the various parameters. If it is not settling down within 2 to 10 seconds, then we'll say that the system is unstable. If the system settles down to a stable operating point, then the system is said to be stable. It is necessary that both small signal and transient stability analysis should be carried out for any system to assess the health of the system. Generally, in the real-time stability assessment, they do this two type of small signal stability analysis. One is small signal stability analysis and transient stability analysis. Through this, we can assess the health of the system, health of the power system. So this is how now we're in the verge of completing the transient stability analysis. So next class we'll see some another approach for analyzing this transient stability analysis, that is called direct method. We'll discuss that in the next class. Okay.